Alright, so this notebook is on hyperparameters and validation sets. The first thing we're going to do is we're going to create some fake data for us to try and model. So we'll just run the cell, create some data, plot it like that. So this is the true data generating function, and these circles are values which have actually been sampled from that function to be in our data set. So now we're going to do the usual. We're going to split our data set into training and testing sets, but for the first time we are going to use PyTorch's random split method to do this for us. So we can firstly, let's have a look at how we do that. That's actually PyTorch random split. So we can look at this method here. So we can use, okay, this is not the one. Have a look here, random split. Cool, here we go. So what does it take in? Well, it takes in firstly the data set that you want to do a random split on, and then the different lengths of the outputs that you want from that. So if we want to get train and test sets of size 15 and 5 respectively, all we do is we'll use torch, which we've imported in the cell above. So we'll do torch dot utils dot data dot random underscore split, takes in the data set which we want to split. So we've got this variable data set here, that's the one which we're going to split, and basically that is a vector of all of these different input values which we've got here, the red dots, and then we want to split that into size 15 and 5. So then we should be able to run that, and then we have it. So now we've split it up and we've randomly split the randomly separated out the examples which we actually sampled from the data generating function into these dark blue ones which are in our training set and these teal ones which are in our training set. So now we're going to train a polynomial model which looks something like this. It has a bias and weights for each weights as coefficients for each power of x up to whatever order we specify, and we're going to evaluate its performance using the mean squared error loss function with regularization. So we're going to penalize it for having large weights for any particular feature, as we've covered in the regularization notebook. So we're going to use this multivariable linear hypothesis, and then we're going to basically, as we've done many times before, we're going to create the polynomial inputs. We're going to create our model with, we're going to create a fifth order polynomial model. Then we're going to train it on our training data. So this is, we've created the polynomial inputs from our train data, which we got by splitting our data set there. And then, basically just going to evaluate the loss and then plot that. So just run that. Get this output. Cool, it looks like it's been fit pretty well over most of the domain except from over here. We can try that out with different powers as well. If we do it with 1, well, it's going to be a straight line, not a very good fit. Let's have a look what else we get. That's the best quadratic fit. Looks kind of cubic, so let's try that. That's a pretty good one. Right, that's got a very small loss. So now let's talk about hyperparameters, what we're actually here for. So you probably asked yourself a bunch of times already, what is the best weight decay coefficient? What is the best value of this lambda weight decay coefficient here? Or what is the right batch size for me to use? Or what learning rate should I use? Or what terms should my polynomial include? And these are all examples of hyperparameters. They're not optimized by the learning algorithm themselves. So gradient descent doesn't update these for you. Most commonly, a parameter is chosen to be a hyperparameter because optimizing it on the training set is not really appropriate. For example, if we had our model automatically learn what polynomial terms to include in the hyperparameter based on the performance on the training set, well then it would choose to have as many as it possibly could, because that means it has a higher capacity, which means it's easier for it to find good parameterizations which perform well on that training set. However, then what will happen is the model will probably fail to generalize. And so this is kind of why it's not appropriate to train the model capacity on the training set. And also the regularization factor, that lambda, is also a parameter which controls model capacity. So that's also something we don't want to train on the training set. And so we choose that to be a hyperparameter. Other times it might be chosen because it's hard to optimize. For example, the batch size is hard to optimize because it means, if we want to test what values are that good, it means we have to both fully train and fully test models for each different possible batch size which we want to try. So why should we not train our hyperparameters based on the model score on the test set? So there's a clue there, is like, you definitely shouldn't do that. Why not? Why not train hyperparameters on the test set? Well, previously we've just been splitting our data into training and test sets, and the test set is used for estimating how well our model is going to generalize on unseen examples. But it's really important that we don't use the test set to make any decisions about the model. We definitely can't obviously train our model parameters, our model weights and bias on the test set, because then we'd easily be able to overfit to those examples which are on our data set. And then when we try some new examples, some totally unseen examples not in the data set, it might not generalize to them because it's overfit. So we definitely can't train our model parameters on that, like the weight and the bias. And so similarly, we also definitely can't train any hyperparameters on that. If we basically trained a bunch of models and then trained a bunch of models with different regularization parameters or different model capacities, and then tested their performance on the test set, well then that would be basically cheating and looking at the answers, because if we're just choosing those hyperparameters based on the performance on the test set, then we're just choosing how well they're going to do on those particular examples, not how well they'll actually generalize. The point of test set is that we test the final model on it just to see how well it generalizes. So we can't test our hyperparameters on the training set because that's not appropriate, as we said by definition, and we can't test them on the test set. So what can we do? Well, just like we previously split our data set into train and test, we can also split our training set further into a final training set and what we call a validation set. And training and tuning your hyperparameters is exactly what this validation set is for. So we'll train our model, we'll train the model parameters on the training set, and then we will optimize and tune our hyperparameters on the validation set. So similarly to above, we can just use the torch.utils.data.random split to split our train data into the final train data and now a validation set as well. So I've pretty much evenly split these, but you would maybe choose a larger proportion of them to be the training data in practice. Okay, then we're going to create this validation function, which is basically exactly the same as a test function, but we're just going to rewrite it out here. And just to show that that's what validation is, it's just testing, but not on the test set. So we're just going to pass it different inputs. So we'll do the same as we've done before, make predictions. So we will make a prediction for that x. Then we'll calculate the loss by doing, so we're doing the mean squared error. So the error is y hat minus y. If we want to do the mean of that, then we can do np.mean, and if we want to take the square of them, well then we should raise this to the power of 2 like that. And if it's going to be yeah, cool, that's going to work. And then in this case our loss also has regularization term, so we're going to need to add np dot sum of the weights squared. So the weights of our model is a vector. We're going to square each of them such that the new vector contains all positive values, and then we're going to sum up those values and add that to the loss function to evaluate the loss. Cool, so we've done that. We split our training set into the final training set, which we're going to train our model weights and biases on, and the validation set, which we're going to test different hyperparameters for. So we can optimize both the model parameters and the model hyperparameters without at all looking at the test set, which is exactly what we want. So now let's just implement a grid search to optimize our hyperparameters. So to start with, we'll initialize an empty grid of zeros. So how do we do that? We do np.zeros, zeros like that. And this takes in a size. Okay, what's the size? Well, I want it to have, I want every, what does it say here? Each row to represent a value for the weight decay param. So how many rows should it have? Well, it should have the number of weight decay params, which we're going to test. So this is just, we're going to make a list of evenly, linearly spaced values from 0 to 1/1000th, and we're going to try 10 different values of them. So len weight decays, and then the second parameter, which is the number of columns which this empty matrix of losses is going to have, is going to be the length of the highest order powers that we're going to test here. So this is the numbers from 1 to 10. It's a list of them. Well, if we wanted to go from 1 from 10, we would actually do it to there, because the last one's inclusive, but highest order powers is going to go there. Okay, so then for each power, we're going to create training features with training inputs with those polynomial features up to that power. Then we're going to find the actual labels for them using this y function, which generates the labels using the data generating function on train data. That's in the top cell, if you want to take a look at that. And then we're also going to create a validation set to actually evaluate these the losses that we care about, right? We're going to evaluate the training losses. Sorry, the validation losses, even though we're going to train on that train data. And then we'll create the model, which has those different orders of x up to the highest order power. So we'll try a model which just contains x to the 1, and then x to the 2, then x to the 3, all the way up to the power of x to the power of 10. And then once we've created the model and the data sets, then we can iterate over the different weight decay parameters for each of the weight decays in this list. And so we'll train a model using with that order, with the first order polynomial and the first weight decay parameter, so that regularization factor lambda that I talked about. And then once we trained it, we'll evaluate its loss using the validate function which we wrote here. And then what's it going to test on? It's going to test on the validation inputs and the validation labels. And then once we've calculated that loss, we'll just put that into the matrix of losses. So let's run that and see what happens. We're just going to wait for that to be done, and then once we do that, we are going to visualize it in 3D. So we're going to plot a surface over with two inputs, one being the different weight decay values, and one being the different order of the polynomial, and then we're going to plot the height of that surface as the loss for that particular parameterization. Cool, so it looks like that's finished running. Now run this and see what happens. Oh, doesn't seem to have worked. Must have been a weird model that we got to start with. fuck's sake. Why is it not working?
What's happening?
Oh, it's just the graph I wanted to show is just not right. Ah, you fucking idiot. That's why. Definitely cropping this bit out. Weight decay. So I actually forgot to put this weight decay parameter there. So if we run that, need to restart the kernel. Run all the cells. Okay, there we go. That's what we're after. So this is the 3D plot of how our validation loss varies as we change the order of the model and the weight decay parameter. And you can see that they do different things based on whatever those parameterizations are. And here I've basically said, okay, find whatever the minimum values in that matrix are and plot a vertical line at that point. So this is what we should use our optimal parameterization. That is, we should use a model with which includes an x cubed term, and apparently we should use no regularization. So it seems to fit pretty well. It seems to generalize there. Cool, that was it. So yeah, you should now understand what hyperparameters are, how they're different from other parameters, and how they can be tuned using a validation set.